Yeah, welcome everyone to the ZPNC stream. I'm Piara Bamra and I'll be moderating this session. For this presentation, we've got Scott Chapman from Enterprise Performance Strategies, and he's going to be presenting on SIS, which stands for Storage into Instruction Stream. This session is 6BH, that's the session code. And as with all our sessions, we'd really appreciate if you can leave us some feedback towards the end of the session. I'll leave a link in the chat box so that you can directly access that. And we'd also appreciate any donations, big or small, to our nominated charities, which is RNLI and the Guide Dogs for the Blind. We're almost at 100% of our target, so if you could help us achieve that, that would be absolutely fantastic. And it would also give you the chance to enter the prize raffle as well. In terms of Q&A for this session, Scott will be monitoring the chat, so please feel free to ask any questions, and yeah, he'll make sure that he answers them throughout the presentation or otherwise at the end. And yeah, without further ado, over to you, Scott.
Okay, thank you very much, Piara. And thank you everyone for coming out today on the last day of GSE UK to listen to my little talk here. So let's see here. Whoops, I clicked on the wrong thing. There we go. Let's see this. So this is the abstract. And I presume you've all read this, and this is why you're here. This presentation is actually kind of my exploration of this particular topic. So it's kind of, I won't say it's a stream of consciousness type of thing, but it is kind of follows along with what I was thinking as I was looking through this stuff. We will have plenty of time in this presentation, unlike most of my presentations where I'm usually rushing at the end to try and cram all the slides in. I have plenty of time with this one, so feel free to throw things into the chat here and make it more interactive. So if you don't know who Enterprise Performance Strategies are, we do ZOS Performance. We have Pivotor, our reporting and analysis software and service, which we use to help people understand the performance and capacity of their mainframe systems. We have education and instruction. We do ZOS performance workshops, which I'll mention on the next slide. We do consulting. So if you have a particular ZOS performance issue you're having, then you can contact us. We'll come in for a couple of days, or we'll do it over Zoom these days, where we'll get everybody in the room, real or virtual, I guess, and discuss your particular situation. It's actually been kind of interesting because we've done more, obviously, over the last couple of years. We've done these over Zoom with the pandemic. And it's actually been kind of interesting because while you lose something from not being in person, on the other hand, it gives us an opportunity to take those 2 days and break them up over time more, which has been kind of useful because sometimes we'll get into, we'll do 4 hours of a session and we get all the background, and then we say, you know what, you need to send us this data and this data, and we'll come back tomorrow or the next day, and just splitting it up actually has been beneficial at times. And of course we present at conferences and so forth like this. So these are our ZOS performance workshops. Our workshops are a little bit different than just straight up classes because we ask you to send data to us ahead of time, and then you can actually be analyzing and looking at that data as you're going through the class. So you're not just seeing abstract examples, you're seeing your real stuff. Obviously, these are, most of these are gone by or is next week, but we'll have these again, of course, in 2022. And understand, if you like what you see, all the performance graphs here are coming from our tool. And if you don't see them in your own reporting tool, feel free to send us a day's worth of data. We're always happy to do a cursory review with you, show you the product, show you your data, and so on and so forth. Also, just want to point out, if you are limited in your reporting ability, we do have while Pivotor is very affordable, we do have a free offering as well. So it is somewhat limited in scope, but we do have some customers who are small or who have been told that we're getting off from the mainframe, and we've been getting off from the mainframe for 5 years and they still need to manage some performance. But so we do have customers that do take advantage of this as well. Okay, but what we're really here to talk about today is store into instruction stream. So what are we talking about here? Well, what the crux of the matter is that modern processors are complicated beasts, right? So while you may think, you may have this idea in your mind that you write application code, be it in whatever language you write it in, that application code goes through the compiler, and there's now basically a stream of instructions that the processor executes in order. That's kind of a fiction. Because the processor doesn't just execute those instructions one at a time in that specific orders. The instructions actually get executed out of order. They get executed in parallel. Now, this is separate from SMT, right? You still only have one thread using the processor at a time, at least from a general purpose engines, and we're not going to talk about SMT. But the idea here is that you have a program, and that stream of instructions is coming into the processor through the L1 and L2 cache. It has to go through the decode, the order, the stage process here, and then those instructions get divvied up into the pipeline. And there are multiple execution units on the processor, so the physical processor may actually have multiple instructions in flight at any one given moment in time. Some of your instructions are going to have to fetch data out of memory. They'll come through the L1, the L2 data caches. And then at the back end, there's the order destage and check process, right? Which basically says, hey, we had all of these instructions executed. We now need to make sure that it appears like we executed them in the correct order, right? Now, this is what allows you to get your performance out of your modern processors, is your ability to be fully utilizing that processor core by having multiple instructions basically in flight. However, there's a number of things that can cause pipeline stalls, right? So if you have an L1 data cache miss or a translation look-aside buffer miss, getting data out of L2 or out of the further caches is going to take a longer amount of time, right? And that may cause a pause in the instructions. You can imagine if there's an instruction down here that's waiting, that needs a result from the load from memory, then this instruction is going to have to pause, right? But there's lots of things that can cause that. And when stalled, there are parts of the chip that are idle, they're basically not doing work. And the whole idea of the out of order instruction is that helps avoid that pipeline stall, right? So you may have an instruction sitting here that's waiting on an instruction load up here, but you may have other instructions down here that may still be executing this, not immediately dependent upon this data. So what are we talking about with SIS? Well, SIS really describes a situation where the code writes to memory that is within one cache line, which is 256 bytes, of the executing instruction. When that happens, that will trigger a flush of the cache line from the L1 instruction cache, which will in turn trigger a pipeline flush. Okay, so basically what's happening is you have instructions that are sitting here in L1, but you just did a store which happens to be to the same area as, your instructions are coming out of here, out of L1. Now all of a sudden the processor has to resolve that situation. It resolves that situation by flushing the pipeline, basically. So this can be a significant performance hit, right? Because we had all these things in flight, and now all of a sudden we're saying, oops, stop, rewind, and do this again. You do this once, it's not a big deal. You do this twice, it's not a big deal. But if you keep repeatedly doing this, right, then this can be, in fact, be a huge deal, because now you're really losing the benefit of all that architecture that is trying to run multiple instructions simultaneously. Now, this problem is really an assembler language problem, at least from a modern perspective. COBOL and Fortran have had issues with this in the past, but by the past, I mean circa the early 2000s, right? So we're coming up on, Fortran, has protected against this since 2002. COBOL version 4.2 had a problem with this, with no opt-in test. I believe this was also about 20 years ago, okay? So this shouldn't be a problem for your high-level languages, unless you have really old high-level language stuff that hasn't been compiled in like 20 years. Of course, some people do have that. So, but in most cases, hopefully that's not the case for you. In most cases, we're really talking about assembler language code here. So the question is, do you have a SIS problem? And if so, can it be quantified, right? IBM came out with this paper, I forget when now, it was a couple of years ago now, and basically came up with a formula that is effectively the percentage of instruction stream updates that required L3 intervention. And what this basically is an indicator of is an indicator of that SIS, that store into instruction stream happening. Now, they came up with thresholds for recommended action, okay? I'm not gonna argue with these thresholds because I can't say that I've seen enough data to necessarily make those arguments. I mean, I trust that they did the analysis and they thought that these were reasonable thresholds, right? In other words, greater than 10%, you know, they figured this should be a top priority. You should really take a look at this. This is significant or considerable overhead. And between 5 and 10% was noteworthy SIS impact. And you might want to, you know, investigate and remediate that on kind of a medium priority basis. Below that, it's kind of immaterial is what they basically are saying here. Note though that this doesn't estimate anything about the actual savings you may see. You know, in some cases that could be significant, but you know, in other cases you might have a high SIS percent during low utilization times, and so do you really care? You probably don't, right? Because there's probably not enough actual impact there to see it. Now, the other side of this is, okay, it's great that we have this formula. We can easily calculate this. We can find timeframes where we have perhaps considerable SIS impact, but how do you find the culprits, right? And that was kind of where I came from this, you know, neat numbers, great that we have an indicator, but how do we find the culprits? So this was some of our initial reporting of the SIS indicator percent. And in this case, we see there's this very regular occurrence here. Now, this is a week's worth of data. And if you look at the timeline, it looks like pretty much every day there's this, you know, kind of spike here. It turns out this spike is around 7 a.m. And so this is kind of actually an easy case because you look at this and you go, oh, well, what's running at 7 a.m.? And if you go back and look at what's running at 7 a.m. every day, maybe you can find, in fact, the potential culprit there, right? Especially if that thing's not running any other time. And that was pretty much the case here. It was pretty easy to pinpoint, hey, we think that's probably the vendor product that's probably causing that spike there. However, this is a single day here, and here we see multiple instances, multiple time frames where we are above that 10% line, and some others above the 5% line. But, you know, once we initially started looking at this, you know, the first question that came to mind is, how much savings are we really talking about here, right? Because if we're, again, talking about low utilization times, maybe I don't care so much. And the other thing was, you know, I did this for both the zips and the CPs. So that's interesting. And in fact, the CPs had very low SIS indicator percentages. And that's been pretty much the case across the board. We really don't see much of an issue with the zips. And even if we do see a little bit of an issue with the zip, do we care? Well, the answer is probably not, because the zips are cheaper for us. Generally, we have more abundant zip capacity than general purpose capacity. And there's not customer code that's running there. It's coming from an ISV. So, I mean, is it possible you could have a zip SIS percent problem that is significant that you want to go back and, you know, beat on the ISV and try and get them to solve? Yes, it is possible, but it's less likely. So again, how can we find the culprits here? And of course, like I've said, look for those commonly running assembler-based programs. And then the other idea here is, well, maybe we could look for high CPIs in the problem times, okay? CPI stands for cycles per instruction. Basically, how many machine cycles on average is it taking to get an instruction done, right? So higher CPIs means we're running less efficiently in terms of we're getting less instructions through the processor per machine cycle. And so we'd like to, high CPIs are an indication of potential performance problems, right? Or it could be an indicator of long-running instructions too. So we made some reporting changes. So first thing we did was separate out the zips from the CPs, because probably I don't care as much about the zips. And then what we added in the background here is this gray bar, which is the processors used. Okay, so this is the number of CPs used by the LPAR in total. Why is it the number of CPs? Well, because where we're getting this data from, that was the easy thing to calculate here. So that was the easy way to express it. In this particular case here, what we're seeing is that during this big spike here, which I mean, this is indicator percent spiked over 50%. So it looks like, hey, there is significant overhead here caused by SIS. We really might want to go find this, right? But if we look at the actual utilization value for that interval, it turns out that it's using less than 20% of a single engine, right? So less than 0.2 CPs. This is on a 6-way machine. So that ends up being equating to less than 3% of the capacity of the machine is actually in use by this LPAR at this time where we have the problem. So what's the maximum that we could save? Well, it would be 3% of the capacity of the machine if the entire LPAR's utilization was just given over to this problem. And we know that makes no sense, right? So we're talking about a tiny percentage of our total capacity that's probably impacted by this. Maybe it's 1% because, hey, this is a very high number here, right? But how much do I really want to go chasing that down? Based on the amount of utilization we have here. If it's happening once in a while, I probably don't care enough to go try and chase that down. Now, if it's something that's regularly happening, maybe I still want to go chase that down because, hey, it's 1%, maybe it's 1% of the capacity of the machine. That might be a plausible number. Getting back 1% is 1%, right? You don't get it back if you don't go find it. But again, if it's something that has just shown up here every now and then and it's not very consistent, then maybe we don't worry about it, right? Now, in contrast, in this situation here, we have a number of spikes that are well above that 10% threshold, and the CPUs used during that time frame is multiple, right? So here we have multiple CPs being consumed by the LPAR, and this is indicator percent is high. So we're not consuming a fraction of a CP, we're consuming multiple CPs, and the SIS indicator percent is high. So these are definitely times where, hey, this probably makes more sense to go pursue these particular intervals, okay? So then the question becomes, well, again, how do we find those things? All right, so, and in this case, when we're looking at this, it's not necessarily the nice, easy, oh, it's always 7 o'clock in the morning, right? It's more diverse times across the week. So this was a little bit interesting situation. If I recall correctly, this particular example actually was a customer who had assembler language code who did have this problem. So this was actually, when we brought this up to them, they were like, oh, that's very interesting because we were aware of this and we had thought we remediated all of that, but apparently we haven't. So this leads us to the SMF30 instruction counter. Okay, so there's an option in SMF PRM called SMF30 count, which enables the SMF30 counter data section. The default is no SMF30 count. And the idea for these counters was, hey, wouldn't it be great if we had a count of the number of instructions being executed? Because if we execute the same code repeatedly, we'll get variable CPU times in today's world, right? So you could run the same batch job with the same input, the same output, and in most customer environments, if you run that batch job 5 times, you'll have some variability in the CPU time. Now, again, depending on the environment, that variability may be relatively small. Maybe it's plus or minus 5%. Well, plus or minus 10% is not unheard of and is not unrealistic. And so part of the idea here was, hey, if we could count the instructions, that batch job is executing the same instruction stream, right, over the same input. So why don't we count the instructions? And that should be a more stable indicator of the amount of work that the batch job is doing, except that it ended up not being stable. And the reason for that, turns out, is that the CPU timers are actually very smart, and the hardware and the operating system have the ability to basically, when the CPU is interrupted and has to go handle an IO, for example, the CPUs can, the CPU timers subtract out that interrupt handling time. So that batch job that's processing that data, it may have been lost the processor momentarily because the processor was needed to process an IO interrupt, which may not have been from that batch job at all. Could have been something entirely different, right? And so that time that the CPU was taken away and was processing that interrupt is backed out of the CPU time recorded for the batch job. But there's no similar mechanism for the instruction counts. So the instruction counts still have basically that interrupt time, the interrupt processing in there, and basically the instruction counts become more variable than the CPU time. So the thought is, even though the section is relatively small, why bother? And so our recommendation for, since it's came out, is, don't bother with this. But maybe it's time to revisit this, right? Maybe it's time to actually say, maybe we should turn on the SMF30 instruction count, because maybe it could help us understand this SIS overhead. So one of the other things we did was we took and came up with a report that basically looks at the CPIs recorded in the job steps during those problem times, okay, during the times where we had a high SIS indicator percent. And the way this particular report works is, now the gray bars back here are the high SIS, or the SIS indicator percent. So here's an interval where SIS indicator percent was above 20, right? And then the dots and lines here are basically the CPI for the job name that was on a step execution here, where the CPI is higher than we'd expect. Okay, overall, you might see a CPI down around 2 on your machine for the overall, CPI for an LPAR. So we expect it in that low single digit type of range. And here we see things that are having CPIs that are 100 times greater than that, right? So these can, even down here, this green thing here, whatever that happens to be, that's running about 40 or so, even that is high relative to the single digit type of CPIs that we expect from the LPAR overall. So the thought here was, well, hey, if we can show you that there's some consistency for the jobs across when we have these high SIS counts, maybe that's an indicator of what the problem is. Okay. Now, the very first thing we noticed was that there were several address spaces that had really high CPIs, right? And these were common even when we didn't see the SIS indicator percent being high. So these are things like NET, the DBM1 address space for DB2, OAM, and the commonality across these things were there were things that tended to use compression and encryption, okay? So your compression and encryption instructions will naturally take a much longer time than just a load register, right? So by definition, those instructions are going to take many cycles to complete. And so it makes sense that those address spaces, those particular jobs, would have a very high CPI. So those aren't really indicative of a problem. Now, if we're looking at this live, you could hover over those individual points and you could see, oh, well, here's a high CPI, but there's low CPU usage, so maybe this is immaterial to me, right? It may be driving some of that SIS indicator percent, but it's probably immaterial to me. And at times, low usage can also drive a high CPI. Why is that? Well, because the jobs or the address spaces instructions and data probably aren't in the L1, L2 cache if it has a very low utilization thing, right? So it's not doing much CPU work. It wakes up periodically, does a tiny bit of CPU work, and then goes away. Those sort of things don't necessarily stay around in cache if there's a relatively long period of time between those dispatches. But we do want to look at for things that appear in multiple intervals and are written in assembler. And then the next thing we did, of course, was, well, let's look at it by program name as well. In this particular case, what we ended up seeing was, hey, there's a lot of cases here where SAS shows up. Okay, so maybe that's an indicator that maybe SAS is involved in our problem times here. That wasn't necessarily the case all the time, but it showed up enough that it was interesting, right? And the reason I'm picking on SAS a little bit is because SAS is an interpreted language, and SAS was one of the original problems that were seen with this way back about 20 years ago. I forget which processor it was came out, and immediately people who are running SAS recognized that their SAS work ran much underperformed on the new processor, right? And it turned out to be this store into instruction stream type of problem even back then. SAS made changes and greatly eliminated that problem. Doesn't mean that the problem is completely eliminated necessarily, but I know back then they had made changes to reduce the problem, right? So I would expect that those sort of things where you're interpreting, you have interpreted languages, you know, could be potentially more susceptible to this. I don't know that for sure, but I could certainly understand where it might be coming from. So can we trust the SMF30 CPI, right? Can we use those instruction counts to calculate a CPI, and can we trust that? And the short answer is no, and the long answer is no, but it may still be somewhat useful, okay? The address space CPI depends on those cycle counts. We already mentioned the variability problem. And, you know, I've heard it said that, well, just ignore the obviously bad measurements. And my answer to that has always been, well, if some are obviously bad, aren't there some who are not obviously bad? And I think the answer has to be yes in most systems. But even given that, I do think that address spaces or programs that consistently show higher than expected CPIs during the times of the high SIS might be worth investigation. I have a couple of slides here just to kind of show you the issue with the variability of the instruction counts. So what I did was I chose a few system address spaces that the idea is that these things are hopefully doing more or less the same work all the time. And so, for example, here I have RMFGAT, and we see it's not using a whole lot of CPU time. It's using about 3 CPU seconds every 900 seconds. So it's a relatively low CPU consumer, but it's relatively consistent, right, throughout the day. And we kind of expect that, right? I mean, it's going to change a little bit based on the amount of address spaces, amount of active work units on the system. So we do expect some variability in CPU time, but it's fairly consistent throughout the day. In contrast, the green up here is the millions of CPU instructions that were executed during that interval. And you can see the instruction count recorded for RMFGAT is quite variable throughout the day. Sometimes we see here that, you know, the instruction count went up, you know, this probably gap here is about 25% increase in the instruction count. Did our CPU time go up 25%? Not even close, right? I believe these sort of variabilities that we're seeing here is really much more related to the issues with the instruction counts in the SMF30s. That is, that those instruction counts can be polluted by things like the IO interrupts that are causing the processor be taken away and doing work for other system-related tasks. Yeah, and in this case too, the other point was that, you know, if you're trying to ignore the outliers, where are the outliers, right? It's harder to make if this spiked up to, you know, twice as much or something, you might say, oh, well, that's an obvious outlier. But in this case, I don't know that there's necessarily obvious outliers. This address space is WLM. Again, not consuming too much CPU, but consuming very consistent amounts of CPU throughout the day. And again, the instruction counts here are extremely variable, again, on a percentage change basis, interval to interval, compared to the CPU time. Here's WLM on a larger system. The interesting point here is that, here we do start to now see some better better correlation between the instruction counts and the CPU time. We can kind of see, hey, look, this kind of follows this, the green kind of follows the same pattern as the blue here to some degree. There's still variability here, right, that we don't see in the CPU time. But at least when there is big CPU time jumps, we do see that there is an increase in instruction counts. So we do know that, hey, the CPU time, increased CPU time does imply increased instruction counts. So that part makes sense, but we also see that, the reverse of that is not necessarily true, right? Increase in the instruction counts does not necessarily mean that we had an increase in CPU time. So, there is better correlation here, but I think the problem still exists, right? So here is another example. This one was catalog, again, a slightly larger address space. And again, here we see better correlation again. Not necessarily perfect correlation, but there's better correlation going on here. Now, in part, this may also be due to consuming more CPU, right? So if you have more CPU being consumed, hopefully the effect of those sporadic interrupts are somewhat less impactful. I also should point out that it depends on the system configuration quite a bit too, in terms of what CPUs are enabled for interrupt, and the good luck or bad luck of the address space of being dispatched on those CPUs and stuff like that as well. Finally, this example was the best correlation that I found anywheres. This was on a smaller system. Again, we see smaller amounts of CPU time here, but you'll notice that the green and the blue are just about exactly correlated here. I think this was the only system I saw a correlation this good on. And again, we have data from literally hundreds of systems every day. I won't say that I looked at hundreds of systems, in part because most people don't have this, the instruction counts turned on, but I did look at several. This was the best that I ever found. And you'll notice here too that the CPI in orange then becomes very consistent throughout the day, which is actually what we would expect, right? So we expect that the catalog address space is probably doing roughly the same type of work all the time, even though the amount of work may be variable in terms of the amount of catalog lookups that are happening in any one given interval. We expect that the type of work that it's doing, the instruction mix, is probably pretty similar from interval to interval. So we'd kind of hope that the CPI would be stable. And in this case, the CPI is in fact very stable, despite the fact that the CPU time is variable. And the reason for that is the instruction counts are following along with the CPU time, and they're not being skewed a whole lot by these external interrupt type of problems. Now, interestingly, and this was kind of the fascinating part for me, this LPAR had only a single logical CP, but it also had a relatively low IO interrupt rate. So having only a single logical CP seems like, well, this is definitely going to be impacted more, because the IO interrupt I know is happening on that CP because there's only one CP, right? But the fact that the address space did relatively low, or the system itself, this LPAR itself, did relatively few IOs, probably contributed to the fact that this was a more stable CPI and a better correlation between instruction counts and CPU time. So again, it comes back to what is the configuration of the system, what is the system doing, all that sort of stuff. So my conclusions are, only worry about the CIS indicator percent in intervals with significant CPU. Okay, if you have a high CIS indicator percent but a relatively low CPU utilization time, you probably have more important performance things to look at. Maybe not. I mean, maybe it's worth spending a little bit of time looking at it, but oftentimes there's probably bigger fish to fry. It's probably not as well. I'm not going to get into that story. Look first at what's running during those intervals. Customers without assembler language application code probably have relatively few SIS problems. Most of the ISV code appears to have been fixed. In most cases, when we've looked at the SIS indicator percent across customers, most customers don't have consistent problems with this. Okay, like I said, that one good example where, hey, it looks like several times during the day and so forth, and does seem relatively high, busy times. Again, that was a customer that actually had assembler language application code that was probably having this exact problem. The other point to this is that it's easy to remediate that code, okay? Because again, the only thing you have to do is make sure you store more than 256 bytes away from the instruction stream. So it's relatively easy to add a guard area to make sure that you're not doing that. But of course, you have to go get the application folks to change their assembler language code, which could be difficult in some situations today, I recognize. We have seen it with a few cases where it does appear to be ISV related code. Again, how much effort you're going to put into trying to convince your ISV to track it down and fix it probably depends on how big of a problem it's causing, right? If it's happening consistently, if you can consistently point to that point in time and so forth, you might have a good argument that you might be able to get them to do something about, but I understand that's going to be an uphill battle too. The SMF 30 instruction counts might help you find the culprits, but they're probably going to be variable to degrees that are not always obvious, okay? LPARs with low IO rates may be less susceptible to that issue, but you can't just assume that high CPIs are indicative of a problem, especially if you know those address spaces are doing things like the compression or like encryption, because those address spaces are going to have high CPIs anyways. And if you don't have a SIS percent problem, I think there's probably little reason to turn on the SMF 30 instruction counts unless you just like taking a look at it. So yes, there's a question from Rich about, you've mentioned COBOL 4.2. Do higher levels of COBOL not show this problem? And yes, my understanding is the higher levels of COBOL, and COBOL 4.2 is very old, but modern COBOL compilers are well aware of this and will not experience this problem. And does the ARC level have anything to do with it? That's a good question. Again, my expectation from what I've heard from IBM is modern COBOL should not have any problem with this. I suppose that it might be possible that if you had a very old ARC level, a very low ARC level specified, maybe it could be more likely. But again, my understanding is if you're compiling with modern compilers, it should not be a problem at all. So what ARC level is very low? That's so for those who don't know, might not know, ARC level specifies what architecture level of machines you're targeting with that compiled code, okay? And to be, I said very low because I don't remember what they all equate to, right? So if you're looking at something where your ARC level, and Rich says the default is 8, and if Rich knows what the default is, that'd be one, or what 8 equates to, that'd be wonderful. If it was something that was equating to back to something in the Z10 or before era, I might be a little bit worried, right? So if this was defaulting to Z9 or Z900 or something, I might be a little bit concerned about those, right? Because the processors have changed dramatically since the Z900 days. If it's targeting a Z10 or higher, I think you're probably going to be okay. And if you're running something, if you're compiling your code with a default ARC level that is targeting something like a Z10, you should look at changing that, right? The only reason you should do that is if you have in production Z10s that you're running this code on, or maybe if in DR you have Z10s that you're going to be running on, right? That's that would be the only good reason for that. Otherwise, you absolutely want to be targeting the arc level that's the lowest of any of the machines that you have or might possibly run on in DR. Okay, and that may be a significant performance improvement right there, right? Because the compilers actually can be fairly smart, and targeting the newer machines that have architectural changes and instruction set changes to make the code more efficient. If you're not targeting those newer architectures and you're forcing the compilers to produce output for a Z196, for example, and not a Z14, if you're maybe running on a Z14 in production or DR, you may be giving up significant CPU times in the application. So, I mean, that's not really related to SIS at all. It's just good practice that you really want to look at doing that. And there was a question, how did you get the data into the very nice charts? Well, again, my thing at the beginning was if you're a Pivoter customer, those come out of our product. If you are a Pivoter customer, this was the slide that says, hey, here's where you find those charts. And again, if you would like to see similar data yourself, send me an email. My email is there on the front page, and I'll be happy to set you up to send us some data, and we can produce a set of reports for you and have a call with you to introduce ourselves and the product, and then give you access to the reports to let you walk through them yourself. With that, I appreciate all the comments, and I'm not cutting off comments at this time. I'm just saying, don't forget to submit your session feedback and become a member of GSE. But if there's any other comments or suggestions, I'm happy to take them now too.
Thanks very much, Scott. Yeah, like Scott said, if anyone does have any comments, feedback whilst Scott's here, please do type away in the chat, and we can answer those. So I'll just give it a few seconds. Well,
absolutely. Like I said, I had this is a surprising presentation for me from the perspective of finishing with 15 minutes left over. 17 minutes by my clock is very unusual for me. So hopefully everybody found something of interest in this presentation. It is somewhat esoteric, but I think that part of the good news out of it was for most customers, it's not a significant problem today, is what we've been seeing. So if you can go home and say, well, hey, it's probably not a problem for me, that may be maybe that's goodness in and of itself.
Yeah, absolutely. Well, we don't have any more questions coming through at the moment, but yeah, thanks so much for the presentation. That was excellent. If anyone does want to follow up with Scott separately, that's his email is on display there.
Somebody found the
yeah,
answer.
sorry, we just got some just a comment from Wendell.
So arc level 8 would be Z10. And if that's the default, that is a very old processor. So the other thing to take from this discussion then, thank you, Rich, very much, is that if you are compiling with those default arc levels and you're on a modern processor, i.e. a Z14, even a Z13, or a Z15 for sure, by all means, you need to be changing that arc level in your COBOL compile processes so that you are targeting those modern machines. And if you're coming from arc level 8, if you have COBOL that is intensive CPU consumers, which is not always the case, right? It's often that the database can be much more CPU intensive than the actual business logic. But if the business logic is consuming significant CPU, and that certainly may be the case, then changing from arc level 8 to arc level whatever your lowest machine that you have either in DR or in production could result in really significant CPU savings for you. So that may be even more important than the SIS discussion, is that discussion right there.
Absolutely. Well, yeah, I don't think there's anything else coming through at the moment. As you've already mentioned, Scott, if people can leave session feedback, we'd really appreciate that, and donate to our nominated charity as well. I've left links for both of them in the chat box. And with that in mind, I think we can end it there if you're happy, Scott.
Absolutely, and thank you for Rich for providing that important input for us. We do appreciate that. So, and thank you everybody for coming. I appreciate you coming and listening to me ramble on about this.
Thanks everyone for tuning in. We hope you enjoy the rest of your day.
Yep, you too.
Take care. Bye bye.